Are you ready to work out this example? I hope so, because you pushed play, didn't you? All right, so let's take a look at this example problem. It says what diene and dienophile has been used to prepare this product, and they give me this structure. How on earth do I go about figuring out what two compounds come together? Do you want me to show you how hard this is? Whoop! There you go. There's the two. That's all I need. Let's wrap it up, folks. Nothing to see here. Go on home. Guys, that's all that we have to do. That's why the synthesis problems for Diels-Alder should be extremely simple, because what I've done is I've targeted the cyclohexene ring, because I know that Diels-Alder forms a ring, and by splitting it in half, I have the two parts that I need for this reaction to take place. Well, if we want to truly draw them out, that's fine. Take a look at this product. Take a look at the two halves. Let's start with half number one. Well, I've got to write it before it rearranged. That's the thing, right? So before it rearranges, folks, it was a conjugated diene system, just like that. We know that we have to have a conjugated system for this thing to take place, and right there it is. We've often said that what happens in this first step is that double bond moves in, this double bond moves out, and then the double bond on the other group moves up. And that connects the ring. So there's group number one. What about group number two? Well, you got to remember this bond had to happen somewhere, somehow. Where did it come from? It came from a set of pi electrons that were located between those two carbons. Remember, I need a alkene or an alkyne, a dienophile for this work to work. So, part two is two carbons double bonded together. And I know that off of this bottom carbon, I have a CH3 because it was drawn. And then up here at the top, I have a C double bond O, OCH3. And I'm drawing them this way just so that I can confirm to you that I've put them on the same side of the molecule. Why did I do that? Because, folks, look at your product. They're showing you that these are on the same side of the ring. They're letting me know some stereochemistry. So that's important. I want to include that into my synthesis step. So I've split this ring in half. Over to the left is my conjugated system. This double bond was really up here at one point, and this bond that connected to the alkene was basically right here at one point. There's my conjugation. Then a double bond was here at some point in time, because that points up to finish connecting the ring. There we go. That's how we do it, folks. That's all there is to figuring out how to make these two things happen. Just some reviews on some examples. Let's take a look at this one. Predict the product. Okay, well, here we see the word excess. All right, so excess means the HBr is going to be added on to every single thing that it can be added on to. So they don't want me to choose between two or more double bonds here. They want me to attack it every single place that I can attack it. So how does this happen? Folks, over to the left is a double bond. We know the double bond breaks. Two sides of attachment open up, here and here. Well, over to the left, hydrogen plays with other hydrogens, so it's going to go there. All right, so there's the first addition. A carbocation has now formed, and this carbocation is not going to shift. It's secondary. If it moves over, it's still secondary. So that carbocation stays where it's at. Let me just erase it. And here we have a bromine to go on in that spot. The same thing's going to happen over here to the right-hand side. That is another double bond. That is a site of reaction. It says extra. So I break the double bond. Two sites of attachment open up. Hydrogen plays with other hydrogens. So it automatically goes to the left-hand side like what we've seen before. And that site of attachment has created a tertiary carbocation. That tertiary carbocation is not going to move. It is very stable. So that is where the Br is going to go. Folks, there's the structure. That's how they got it. That's how they formed it. Here's another one. This time it doesn't say excess. Just to recap, that means you've got to pick. This is an isolated alkene. So no delocalization is going to happen here. I really do have to pick one or the other. Well, as we've said before in the previous video, if this double bond breaks, a secondary carbocation forms. If that double bond breaks, a tertiary carbocation forms. And we said tertiary is more stable. So therefore, if the molecule is going to have to pick one or the other, it's going to pick one that it feels more comfortable breaking. And it's the one to the right-hand side. So the one to the left is not going to get touched. The one to the right-hand side, double bond breaks, two sites of attachment open up, hydrogen plays with other hydrogens, and folks, Br goes in that location. Here's another one. Here we have a problem though. Double, single, double cause you trouble. There's my delocalization. So I'm going to get two different products, and that's what you see over here to the right-hand side. And the first one, I'm just going to add like normal. I'm going to add the HBr to this molecule. Do I add it to the carbon double bonded on the left or the carbon on the right? Well, it doesn't really matter. They're equivalent. These two are groups. That represents the same group, so it's a symmetrical molecule. If I look at the way that these bonds are organized, folks, if I break a double bond here, well, I'm going to get the same choices as if I break the double bond on the right-hand side. There's no difference there. So I'll just choose the same one that the reaction flow did in the problem, and I'll just choose the one to the left. I mean, that's typically what we do. It's like reading a line or a sentence again. So I'll look at the alkene to the left-hand side, break it, two sites of attachment open up, hydrogen goes on one side, and Br goes on to the other. And there you go. So there is to it. That's how I got the 1,2 addition product. Why did it happen that way? Well, out of these two choices, you could have said, well, what if I put the bromine on the left and the hydrogen on the right? Would that be the same thing? And I'm going to say, no, it's not. And it really wouldn't prefer that. And the reason is because two different carbocations are going to get formed here. The first carbocation, if it forms here, well, that's a secondary carbocation, right? And then if the carbocation forms there, well, you're going to look at this and you're going to go, that's a secondary too. No, it's not. This is an allylic. Carbon, double bond, carbon, carbon. So the allylic carbocation is slightly more stable than the true secondary carbocation, and the reason is because of delocalization. So that is why we automatically put that hydrogen to the left-hand side, putting it here, because this forms a more stable allylic carbocation. Keep in mind, hydrogens play with other hydrogens, and in this scenario, both of these carbons had the same number. So the hydrogen really didn't care as far as who he plays with. The issue that drove this decision was the carbocation stability. And it's actually what drives the decision every single time anyway. So we see this particular molecule. We know that bromine is going to have to go here because a allylic carbocation has formed at that spot. Now delocalization is going to happen. So up here at the top, I'm going to just redraw this. I'm going to do CH, double bond, CH, CH, double bond, CH. All right, so there we go. That's what they gave us. Well, delocalization can rearrange. A double bond can move toward a double bond. And it really doesn't matter which way I electron push these. I can go and push them to the left or I can push them to the right. It doesn't matter. It's a symmetrical molecule. So at one point in time, this carbon with the double bond on the left is going to go, well, you know what, carbon, I'm tired of you having it all. So I'm going to get rid of the double bond. I'm going to flip it over to the other side of the carbon because electrons can push toward other pi electrons. That carbon is now overwhelmed and it says, uh-oh, I got to fix myself, so I get rid of that. And those electrons have to be pushed onto the carbon next door, which creates a negative. And then over here to the right-hand side, this creates a positive. Well, when I add HBr, folks, H is going to go to the negative because hydrogen is positive. So a CH2 is going to go there. It gets rid of that negative that I have just put onto the molecule. And the Br goes onto the other carbon, and we call that the 1,4 addition because that is the first and fourth carbon of the delocalized system. There we go. You're looking at this product over here to the right, and you're going to go, well, that doesn't match that. Yes, it does. It's the same thing. It's a symmetrical molecule. I can flip it around. No big deal. The way that they've drawn it, I would name this the same as I would name that. If you do not like that, then look at this. I could have chose to push the electrons the other way, right? This double bond, and let me go back to the original first. So this carbon decides, you know what, I don't think I want this double bond there. So, look at me. All right. So it's going to erase that double bond. And when it does, it shifts it over here, and it takes the electrons away from that carbon. So I can put the positive there. That's okay. This carbon makes the decision, well, you know what, I don't like these, so I'm going to have to push those electrons to the left, and that creates a negative. So the H comes on, the H goes here to take care of that negative charge. There we go. And then the bromine goes on to the positive carbon because it's negative. That's where it wants to go. Now that does perfectly match what they've done over here to the right-hand side. Doesn't matter. You could have went left, you could have went right. It doesn't matter. It's a symmetrical molecule. You would have ended up with the same thing. Next one, they give you a Diels-Alder. Notice it's a double, single, double. So here is my diene structure. That's all there is. Nothing more. This molecule to the right-hand side, this is a carbon double bonded to a carbon. And off of one of these carbons, they did it up, but I'm going to do it down because I can. I'm a rebel. Look at me. It's going to give you the same thing. It doesn't matter. So here's the proper template for the Diels-Alder. And over here to the side, I will start off like this. That double bond moves in here. This double bond moves out to connect to that carbon. This double bond moves up, and that connects the ring together. Down here at the bottom, I would draw a carbon, double bond O with an R. These two are the same molecule, folks. There's no difference. You could have put it up, you would have gotten credit. You could have put it down, you would have gotten credit. Doesn't really matter. So, I'm happy to say that's a wrap. So the purpose of this lecture, if you were paying attention, was number one, introducing delocalization. All right, what is delocalization? Why is it important? Number two, then we moved on and we had to identify the delocalization in a molecule if it could happen. And we talked about a couple of rules in order to help us make that decision. Like double, single, double cause you trouble. Number three, then we moved on and we talked about new carbocation additives. This was the benzylic and the allylic carbocations. And we put them into the typical lineup that we've seen before. No difference. After that, We then went back and we revisited alkene reactions. But this time, there was more than one double bond. Sometimes there were two. We had to pick between the two. Sometimes there were two, but there was delocalization involved. And delocalization rearranged the molecule, and we formed two products. And this is where we got R12 and R14 additions. And then finally, number 5, we left off with this idea of a Diels-Alder reaction. How do we put two pieces together to form a ring? Or how do we take a product, split it in half, and figure out what reagents were used in the very beginning? Pretty simple, right? If I go back to this last example and they give me this and they say what reagents were used in the beginning, I look at this ring and I split it down the middle and I take this half and I'll say, well, that had to be my diene, and there we go. And then over here to the side, I've got to keep in mind that that bond and that bond is not there. That came from the double bonds of the diene. So this carbon and that carbon was double bonded. There is my alkene. And then off of that was a C double bond O with an R group. There's the two reagents that we needed. That's all that you have to do to solve those types of synthesis problems. Don't let it get more complicated than that. All right. So that's it of delocalization. It was a little bit of reaction. It was a little bit of review of other topics. And folks, if you can feel it, it's all kind of coming together. And maybe it's an avalanche. Maybe it was an avalanche a couple of weeks ago. But I'm not going to scare you off. But it can get worse. Yeah, that's right. So we've got a couple of lecture modules left. These are all reaction-based lecture modules. It's going to use little nuggets of information that we have built upon this entire time. We're going to constantly look for delocalization. We're going to constantly look for stereochemistry. We're going to constantly look for alkenes and alkyne reactions. And then we're going to throw new reactions in on top of that. We're going to have to go through and name. We're going to have to be able to go from a name to a structure. All of this is building up. And I told you this from day one. And in the next couple of lectures, you're going to see what I'm talking about. So good luck on this lecture module. Good luck on the Blackboard assignments. Good luck on an upcoming test that's going to be pushed out like electron pushers for delocalization and stereochemistry. So if you've got any questions, you know how to get in hold of me. You know how to contact me. That's what I'm here for. That's why I get paid. So use me. Until then, I'll see you on the other side of the chapter when we begin substitution reactions.